course website already. You can enter it from my personal webpage. But there are two mathematical physics. You are mathematical physics 1. As you know that I'm simultaneously teaching the mathematical physics 2 for the sophomore. And this is our webpage. I list on this page all the our material, including the PowerPoint PDF of the PowerPoint files, and you can notice there's a recording for the class. Okay, from this time, if you plug in, it's connected to the video. Yeah. So you'll see the video. So that means you can access the lecture whenever it is convenient for you. I hope it will help you prepare yourself for review this material at home. Okay, so mathematical versus 1. Okay. So second class, we're starting to cover the decay equation. Last week, we started already with a short introduction, or it's a short introduction about the topics I'm going to cover in the whole semester. So including the my contact and work the website, our textbook, I mentioned a little bit about why mathematics is important for physics. The relationships is very special one. Not just they're important to each other. It's so interconnected. We can almost say, that's why we say there is a mathematical physics and there's a physical mathematics. Okay, they are so intertwined. The reason is very simple. That's just you can check. Just a minute. Let me check how that happens. Okay. I thought we were in Iran. But I have to I guess I have to. Oh, but this is emergency. The emergency power generator is running. So I'm not sure if this light is permanent. So there must be a power outage in the area or on the campus. So now, what am I going to do? I probably need to read. Any question about the class? I'm rebooting the computer. 有没有什么问题 ？You can 怎么去那个网页啊？这是退休教授嘛？你要找专任教师，找专任教师找我的照片，点进去就有 personal。So you smell the gasoline smell. So there's an emergency power generator. So I'm not sure the power will be permanent. Anyway, so for some students, you still don't have access to the course website. Here's the address. Okay, maybe you want to take a picture. Oh, this is the address. You don't need to go through the whole process. You just need to type in the website address, so you can access the website. Any question about the class? Suggestion? So mathematics is so important to physics? Because the creator speaks the language of mathematics. Okay, I'm the creator, actually. We're not sure there is a creator or not, but we are sure that all the physicists speak the language of mathematics. Okay, so last week we talked about how the physical law is the most important part of the physics. For example, we reach this page. Here I list all the physical law until, I should say, before the quantum physics. And you can see clearly all the objects of these laws are mathematics notation. We are not biologists. Biologists, the object is real life. Okay, so when you talk about a cat crying, we're really talking about a real cat crying, right? But what is E? I cannot tell you that this is E, electric field, right? So the interesting thing about physics is that our objects are mathematical notation. And these mathematical notation denotes some quantities we can measure about the real life, the real objects. For example, here, maybe I should say, for example, here the F. F is the force. What is force? Force is the force a real object will experience if you fall from a height, when apple falls from the tree to the ground. Okay, so we are talking about the real object. However, when you want to describe it, calculate it, predict it, and manipulate it, you need to translate a real life quantities, which is measurable, to a mathematical abstract quantity, which is calculable. Okay, so there is somewhat a disconnect or relationship between the mathematical notation and the real life measurable quantity. So that's why, and then the physical law are about mathematical objects. Okay, mathematical notation, mathematical symbol, whatever you want to call it. We are talking about F. Okay, so you can see clearly all our physical laws are made with the mathematical notation. That's why we say the classical physical law is written in the language of mathematics. Okay, so that's why that's the first the reason why the mathematical physics or physical mathematics is important for your learning in physics department. But there are another reason. And there are second and third. The second reason is related to the thing we are going to talk about in the first semester. I told you next week. In the first semester, we'll start with the notion of equation of motion. Okay, to be put more. Today and in 15 minutes, I'm going to give you a review of what the equation of motion is. So for those who are familiar with the notion already, so it's all right. I talk about equation of motion, which is the equation that controls the path of an object, a particle actually. And the equation of motion is the physical idea, but the mathematics, it takes the form of a differential equation. Let me write one for you. Simple. The d squared x dt, so that you have some concrete picture in your mind, equal to m minus kx. And most important equation of motion, most important equation of motion in the physical world. That's the equation of motion of simple harmonic motion. When you attach a particle of mass m to a spring of constant, electric constant k, then this is the equation of motion that will describe its motion, right? And it's clear from appearance, this is mathematically a differential equation because there is a differentiation to the second order, right? And it is equation, of course. So let me introduce the idea, differential equation. And it's an ordinary differential equation, but because it does not involve any partial differentiation. Okay, we'll come to partial differentiation very soon. But first, we'll talk about the partial differential equation because, the ordinary differential equation, later will be abbreviated as ODE, okay? Ordinary differential equation is too long to pronounce, okay? I'll just say ODE, ODE, ODE. You have to know what ODE is. Ordinary, this time, ordinary differential equation, like this, okay? So, the first subject of our first topic of our first semester, ODE. In Chinese, 常微分方程式, okay? I'll start with the ODE of the first order. The most famous one is a decay equation. That's our subject today. Then I'll move on to the ODE in the second order. Of course, the most important is the simple harmonic motion. And then I will introduce some variations of this simple harmonic motion by adding a force, a periodic force, especially by adding a damping force. And then you will see this equation becomes more and more complicated, but involve more and more mathematics. And then after, so after that, we'll introduce coupled simple harmonic motion. That means that I will put one spring together with another, and maybe put it between two walls and put a mass here, a mass here. This is a typical coupled oscillation. It's an oscillation, of course. And it's coupled because this spring will relate the force of this spring will not just exert on this one, it will also affect this mass, right? So the technical words is called coupled simple harmonic motion. And mathematically, it is systems of second order ordinary equation. 方程组 in Chinese. In Chinese, it's not just one equation, but systems of 方程组. Okay, so we are writing two equations. That's the easiest way to put it. Okay, so 方程组 ODE 方程组, and then you will see very soon. And this, in order to solve systems of second order ODE, we will introduce matrices and vectors. It's so simple. If you but that's some of the mathematics you have already learned in high school, right? In high school, you will tell you that if you want to solve systems of algebraic equation, you use matrices and vectors. For those of you who are not familiar with this idea, of course, I will review them at the moment, at that time. Okay, but that's how we will try to solve the systems of second order ODE by using these familiar idea, maybe from your high school. And then you will see that in order to solve second order system ODE, you need a very, very new and very, very important, almost the most important idea of the whole course, eigenvalue problem. Okay, you use eigenvalue problem to solve this question. Okay, so this is the first key word of our first semester. Okay, up to here, any question? So couple simple harmonic motion. So it will last about 4 weeks, about a month, maybe a little bit longer. You see that I told you that this course don't have a really fixed schedule. I can go slow because it's in English. Okay, so if you have any question about what I say, please raise your hand. Okay, I can go slowly. Of course, if you don't raise your hand, I assume that you understand everything I say. I'll just push on and push on, push on, push on. I'll go faster. So in order to slow me down, please raise your hand so that I know you don't understand. Maybe you don't quite get. I shouldn't say you don't understand. You of course understand something, but if you don't quite get a certain idea, a certain term. Maybe it's my mistake. My English is not good. So if it's my mistake, then tell me that I don't understand, I don't get this idea. Tell me more. I can always spend about 2 minutes to explain any idea. For example, you can just ask me what is matrix. I will say, wait, let's wait until 2 weeks later, for example. Maybe not every one of you are familiar with matrix. Then raise your hand, tell me, no, I don't understand matrix. Okay. Although I may not answer you at the moment, I will tell you that in 2 weeks you will see. Okay, but that helped me to understand what you understand. Okay, how? Now, so again, we don't have a fixed schedule. We don't need to rush. The only purpose of this course is for you to understand something. Okay, if you don't get it, you don't get it. 我没有损失 ，You have to remember, I don't have it. 我没有损失，损失的是你们。所以再一次，你们是主动者，好，在这个课堂上面，啊 ，You are the actor, not me. I'm acting, but you are the actor. You are the stakeholder. 好，你至少是这个课堂这个 process 的 stakeholder. Then, where am I? Okay, so metrics. That's the first 6. Maybe I guess I'll probably spend 2 months. Then we'll take a continuous limit. Okay, continuous limit. What do you mean by continuous means? Not just 2. We can get 3, 4, 5, 6, 5, 7, maybe 10 to the 23. 10 的23次方。In Chinese, 照照. I finally understand 10 to the 23 is 照照. So I know how to call it in Chinese. There is a name for this huge number. It's a huge number, but it's what happened in real life. Remember, if you look at this desk, the atom in this desk, 照照, 10 to the 23 atoms is involved in this desk. Okay? Therefore, this is a huge number. If it's a huge number, then I can take a continuous limit. That means the separation between 2 particles are really, really, really small. Okay, so that it does not become a colossal thing. If the size is fixed and you have 10 to the 23 照照个 atoms in it, the only way to do it is the separation is really small. So small that you cannot separate them. It could look almost like continuous. That's why you call continuous limit. Continuous limit. Okay, so in turning from a coupled oscillation to a continuous medium, 一个连续的介质 in Chinese, 一个连续的介质 we call it continuous medium. We go from Newtonian mechanics to solid state physics. Okay, 这叫做固态物理学。solid state physics. Because that's what we get is it's a tool to describe real life. What real life? Solid state. Any solid actually is a continuous limit of coupled oscillation, right? Oh, we haven't told you how we're not going to do that. There are some subtlety involved in a very simple words called continuous limit. There is mathematical subtlety. However, that's the idea. Okay, physical idea. Okay, then if we have a continuous limit, then we get an equation. Don't forget what we are doing is to solve the equation of motion for coupled oscillation. And if you take the continuous limit, we are getting the equation of motion for disk, for solids. So an equation of motion for solids is called wave equation. It's called wave equation. Okay, so that's the logic here. So whenever, and the wave equation is the most important topic of our first semester. Okay, you can almost say we devote the whole semester to the study of wave equation. The reason is simple. Let me see if I can transfer. Yeah. This is the wave equation. It's the wave equation. Why is wave equation so important? The reason is simple. I think I talked about this part last week. However, it's so important, I want to emphasize it in 2 minutes. Again, the wave equation 波方程式 is so important because it underlines all the phenomena you can remember, which is called wave. 所有的任何的现象，只要你够格，称之为波。The underline 它底下的方程式都是波方程式。All the wave phenomena that are qualified to be called wave is underlined by this wave equation. Be it a surface wave, be it a surface wave, be it sound wave, be it string wave, be it sound wave, and I'm repeating myself, sorry. Electromagnetic wave, 地震波. I don't know how to do it in English. 地震波. Okay, so all the things you can call it wave are actually described by the same equation, controlled by the equation. And you can use this equation to predict how they propagate. See, but remember, these are all different. I have to emphasize this. I emphasize they are the same, but I have to emphasize they are so different. Okay, for example, sound wave, it happens in air. Air is not even a solid. String is a solid. So you can see immediately how different the two phenomena, underlying fundamental phenomena, are different. Medium are different. Not to mention electromagnetic wave. Electromagnetic wave actually do not exist in any material. It exists in vacuum. Even, remember, we can see the starlight from far away, and that starlight from far away travels through the whole space without anything, right? So that's why you immediately realize the electromagnetic wave can propagate without any medium in vacuum. And that's so different from all these other waves. All these other waves at least need some medium. Air, again, string, water, whatever. But electromagnetic wave does not need anything. However, they are all described by the same wave equation. So I say this is identical equation of motion for all the wave phenomena. The point is, if they are different phenomena with the same equation, you say identical equation leads to identical solution. Mathematics dominate. 数学赢了。Mathematics win. Because even though the phenomena are different, the equations are the same. So the solutions are the same. So you see wave in sound, you see wave in string. When you see wave on the surface wave. It's oscillating thing. That oscillating thing almost like a couple oscillation oscillating. Right? So that's why you see a similarity between dot, although the fundamental materials are so different. Okay? So you see the irony here, I hope. Okay, so where all the wave systems have identical solution, so that gives you a very, very strong tool to understand nature. Because you only need to solve the equation once, and then the solution applies to all of them. You don't need to do it every time. That's the power of mathematics. 数学的力量在这里. You do it once, you apply it all the time. We do it every day. For example, 1 plus 1 equal to 2. Of course. And you don't need to do this calculation every time when you see 2 apples, 2 oranges, 2 cars. You don't need to do it again because you immediately say, oh, there are 2 oranges, there are 2 cars. But actually, you are doing 1 plus 1 equal to 2, right? But you don't need to do it every time 1 plus 1 equal to 2 because the solution has to be the same. Get it? Okay, so that's why the mathematics are so important. That give you the power that you don't need to repeat the thinking every time. Okay. So finally, the last time, all wave systems have identical solution. Then how to do? You actually see if you in high school physics, probably some of you have already seen this solution. Actually, this solution is fx minus vt plus gx plus vt. It's probably not necessary material in high school physics. But if you have seen this, we will usually say, this is a solution that propagating to the right, this is a solution propagating to the left. Anyway, but any of these phenomena is described by the same thing. So in Chinese, we have some basic character from this equation that apply to all the wave phenomena. Sorry, I have to put it in let me put it in English. But you can read it in Chinese. The waveform will propagate with constant speed. And the waveform does not change during the propagation. And also the superposition principle. The two waves superpose. these three features are applied to all the wave phenomena. Okay, and then actually we even have a very concrete solution form for the solution. Okay, wave equation. So that's a wave equation. But wave equation has a different kind of context. Okay, I should say context. The context first one is what you have seen here. I call it usually the ocean. Okay, ocean means we have medium. Wave will happen on the surface of it, but there's no limit. Sorry, no boundary. Better the words. 没有边界啊。Okay, ocean, of course. So a wave traveling like a boat could travel forever, right? However, the same ocean, no, this is not ocean, it's water. The water and ocean are the same. So if this water is contained in the aquarium, yeah, aquarium, I almost lost the word, 水族箱. There are two boundaries. I should say wall. It's strange to call it boundary. Walls. Okay, so that means if you apply the same imagination to this aquarium, one way traveling this way, one way traveling the other way, but soon that one traveling to the right hit the wall and comes back. So join those flying to the left. Oh, okay, so there are people, you see? I don't have a picture, but you know, you usually call it 驻波, standing wave in high school physics. It's called standing wave. In this kind of situation, it's not so easy to use this picture. A wave flying to the right and a wave flying to the left because they are reflecting and mixing with each other, superposed into each other. It's hard to track. So another way to study it is by looking at the standing wave mode. Standing wave mode. In Chinese, 驻波态. I think you learned it from high school physics, 驻波. But you probably don't understand why it's so important. Okay, because it's the wave system in an aquarium. Be more professional with boundaries. Wave system with boundary, then you got basically a string waveform. String waveform very simply has a very beautiful, has two features I can promote at the moment. First of all, it oscillates, again, oscillates, right? For example, this is n equal to 1 standing wave, n equal to 2. I'll go into detail when we reach this level, and then this will oscillate from high school physics, right? They will move up and down, and every particle on the string will move at the same time, at the same stage. So it's almost like this. It's almost like oscillation. Actually, when I reach the continuous limit and wave equation, I will single out the similarity, the correspondence between the standing wave and the oscillating mode of a spring oscillating system. Okay, so let's call it oscillation system, 震荡态，震荡系统。Okay，所有的波 with boundary is oscillating system. Put in more in Chinese, in English. Every wave system with boundary are oscillating system. 所有的波只要有边界，它就是一个震荡形式，就是一个震荡态。Okay, that's the first feature I can promote. The second, this form, we call standing wave or oscillation form, whatever, they happen discretely. Discretely means it does not occupy continuously. 它不是连续的。Because the wavelength, the half wavelength has to be, half wavelength has to fit into the two walls. So you remember that the length must be the half length times n, a numerical, the natural number n. But n is natural number, so it could not be 1.2, it could not be 1.3, it can only be 1, 2, 3, 4, 5, 6. So these modes can be identified by a number which is natural, 1, 2, 3, 4, 5, we call it quantum number. Quantum, this word first appear here, this quantum number, because it does not happen continuously. It can only be 1, it can only be 2, it cannot be 1.25. See? Okay, that's a feature that will feature prominently in quantum physics. Okay, so enough for wave system. So I hope that give you an idea. I will put it what concepts and skill and mathematics I will put into the first semester wave equation. Okay, remember again, final time, wave equation. When we study wave equation, we are not just study a string. We are studying all the wave phenomena, including most important to you, electromagnetic force, electromagnetic wave. Electromagnetic wave is the most important wave in physical world. Okay, so important you use it every day, right? Electromagnetic wave. And you also know that light is also an electromagnetic wave. So you use this since you are an infant. 从婴儿就开始用电磁波了嘛，对不对？ Your eye. Okay. Oh yeah, of course your sun. So you use sun when you are infant. So wave is everywhere. Where is everywhere in physical world. So this semester is very, very worthy because you study once and apply to all of them. Okay, that's the second reason why physical mathematics are so important. But the third reason, because up to here, all the physics I'm going to describe to you, we call classic. Classic means before 1900. Before 1900 means Newton, the typical figure you will think about great physicists, Newton, Galileo, Newton, and Joe, and whoever, Maxwell, and the old guys. And then 200 years ago, we are now in the 21st century, isn't it? So we're entering the quantum world. The world is quantum. The world is quantum. So why spend a whole semester to a phenomenon that's that old? Isn't it right that we look into the future instead of the past? So you would say, let's skip all the classical physics. Let's go directly to quantum mechanics. Yeah, that's the way I'll do it. So in the second semester, I want to smuggle in quantum field mechanics. So, and what is quantum means, everybody probably know already. If we divide the material world into smaller and smaller and smaller units, actually we can get very, very, very small particles that compose the whole world. And what I mean is quark assemble into proton and neutron. Proton and neutron assemble into atomic nuclei, and then it acquires some or one electron and becomes atom, right? This is the carbon knowledge, so everybody know already. But let me emphasize, this is actually a very, very powerful idea, and actually goes very, very deep. Deep means, you see that the atom, the size is about 10 to the minus 10 meter. 10 to the minus 10. Again, another Zhao. So from our natural world to atom's world, there's not too much in between. From our world to the atom's world, Zhao. The ratio is 10 to the 10 minus 10. It's a huge gap. It's a huge gap. This huge gap is actually very important to our various understanding of physical world. For example, statistical physics, but not my topic. 所以这个鸿沟有这样子的远，事实上非常非常的重要。That's why we didn't discover atom in our daily life. Tell me, what phenomenon in daily life you will find atom inevitable? No, you didn't notice atom until all physicists didn't notice atom until 1800. And actually, it's the chemistry taught us The world is composed of atoms, right? 所以日常生活你没有看到有原子存在，为什么？很简单 ，10 to the minus 10 is a huge gap, okay? But it's a huge gap means all these particles, electron, it's really, really small. You cannot see it, and they could be very, very different from our daily world. Their world could be very, very different from our daily world. 电子的世界很可能跟我们日常的世界非常非常的不一样。If you guess this, and you are right. 真的，在这个微观的世界 ，we call it the microscopic world. 好 ，the physical law obeyed by the microscopic world is called quantum mechanics. They are so different. Mark my words. They are so different. And it's almost unthinkable. It's almost unthinkable. So I think that's here. I have this transparency. Feynman say it's 1960 already. 每个人都知道 Feynman 是谁吧？哦 ，Feynman 是 the best, the most exciting physicist ever exist. Feynman once say in his lecture, I think I can safely say that nobody understands quantum mechanics. Come on, 1960. 1960. In 1960, physics has been using quantum mechanics for 30 years, over 30 years, and predict so many things, so much things. I think I have transparency. We predict so much things with such accuracy. Here, we can calculate the magnetic moment of an electron spin to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 digits. Our physical prediction, calculation prediction are totally the same with experimental observation data. We can calculate so accurately, but come on, Feynman, nobody understands quantum mechanics. So let me say, it's so different. Oh, okay. Tony Z put it in this way. Those who are not shocked when they first come across quantum theory cannot possibly have understood it. It's the same as Feynman saying. 你第一次看到量子力学的时候，如果你没有吓一大跳的话，你也不知道你在看啥，你根本不知道你自己在看什么。That's the way physicists would describe quantum mechanics. Okay, quantum is so different, it's so exciting, and of course, it's so useful, right? It's so useful. Without quantum mechanics, there is no semiconductor. Period. Without quantum mechanics, there is no semiconductor. You cannot do semiconductor using Newtonian mechanics. Simple as that. 没有量子物理就没有半导体。That's why so quantum mechanics, quantum physics is so important. So why don't we look in the future and if we go to quantum mechanics course right away, just abandon this class, sayonara. Everybody goes to quantum mechanics. And 为什么我们要学数学物理？假如我们学的都是200年前的事情 ，Why do we need this class if all the things are 200 years old? There is reason. The reason is that The reason is that to describe the quantum world, we need an equation of motion also. Okay, and it is a wave equation. I'll come back to explain why we need a wave when we do electron physics. But let's go to the solution, the conclusion first. We need a wave equation, so-called Schrodinger equation. This is Schrodinger. Schrodinger is a man. Okay, womanizing man. Okay. Anyway, he is a physics. I think active around 1930 to 1940. He wrote down a Schrodinger equation and described the whole microscopic world. Just like F equal to ma, the Newtonian second law, dominates the whole classical physics. In classical physics, go anywhere. The first thing you do is to write down the F equal to ma, right? 在古典物理里面，不管你解什么问题，第一个就先把 F 等于 ma 写下来嘛 ，right? Isn't it right? And I could semi-safely say in quantum mechanical world, everywhere you turn, you write down a Schrodinger equation. You write down a Schrodinger. This is not totally right because later you will see that we have some even more abstract and useful power mathematical tool to transform this wave equation into more abstract, with sometimes called operator form. Operator formalism of quantum mechanics, but that's a senior level the quantum mechanics. At the introductory level, every problem you turn, the fundamental question, the fundamental equation, just like F equal to ma, is Schrodinger wave equation. Oh, so it's a wave equation. And if you look at the equation and compare to, you still remember the wave equation several pages before? You can see clearly between them, the similarity between them. On the left-hand side, a partial differentiation with x, second order. On the right, a partial differentiation. For classical wave equation is second order. For Schrodinger equation is first order. So there is small difference. First order, second order. However, they are almost identical partial differential equation. And let me tell you, the method to solve them are almost identical. That's why in due time I will tell you, and this equation is so successful. It can calculate the energy level of the hydrogen atom. 氢原子的能阶. It can actually calculate the 氢原子的能阶 using this Schrodinger equation, wave equation. And I didn't show, what I didn't show is that inside the derivation, all the techniques are the same as the wave equation I will introduce this semester. So this semester, the first semester is not useless because all the technique you will learn could be applied to the quantum world and applied to your future career. Is that clear? Let me put it in Chinese. 你这个学期所学到的古典的科学，古典的波方程式的所有的数学技巧，不是白费的。你说200年前的事情，我干嘛在意？因为很简单，到了量子力学的世界，你所有的技巧，它还是一个波方程式，所有的技巧你都可以搬到这边来，类似度97%，数字我随便编的啦，但你可以知道有多相似，在技术上面几乎完全一模一样。OK， so that's why we spend the whole semester on classical wave equation because what you learn not only apply to all wave phenomena, it will be applied to quantum Schrodinger equation. And then you will say, 我看是到这里。Yeah, so let's say, so classical Newton mechanics, the F equal to ma, but the quantum world, Schrodinger equation. And when we reach, and let me highlight a little bit the similarity between Schrodinger equation and the classical wave equation. See, this is the paper by Schrodinger, the Nobel Prize winning paper. He said quantization as an eigenvalue problem. Eigenvalue. Told you that's the technique I'm going to use in classical wave equation, isn't it? Yeah, the same kind of eigenvalue problem. Energy quantization. This is energy quantization. I haven't have time to tell you in more detail, but I told you in classical physics, we have a discrete distribution of the oscillation mode. 刚讲那个驻波是 discrete 嘛，是一个的 almost quantization. So that's the origin of the quantization in Schrodinger equation, and also the origin of energy quantization, angular momentum quantization. In the quantum world, almost all the physical quantity are quantized. Quantized means, for example, E is equal to h times nu times n. Okay, that's the energy for a quantum simple harmonic motion. N is 1 to 2, Okay. Quantized. So you write a picture, it comes like this. Okay. That means this N could not be 1.2, could not be 1.5, it can only be 1, 2, It's called energy quantization. It's so bizarre. When physicists first notice this phenomenon, they are shocked. They are shocked. Planck, in 1900, is the first one to propose that for oscillator connected to a quantum system, the energy is quantized. Couldn't be. We all know what simple harmonic motion is. It is a mass connected with the spring. And when you stretch the spring and let it go, it oscillates. Energy stored, right? But the energy stored is proportional to the amplitude. 能量储存是跟你的 amplitude 振幅是成正比，平方成正比嘛。That means you can adjust the point, you release it to adjust the energy, right? Whatever that value you want to assign to the simple harmonic motion, you just by adjusting the amplitude. But no, Planck told you that's not true. Why it is not true? Planck doesn't know what Planck didn't know. It was only known after Schrodinger and all the other people start to write the quantum mechanics, field mathematics more concretely. 20 years later, okay, energy quantization. And the answer is simple. As Schrodinger highlight in the title, quantization is eigenvalue problem. Why quantization? Because it is eigenvalue. Of course, you don't understand what I'm talking about, so that's why you need a course for a whole year. The second semester, in the middle of second semester. Okay. And then, what else? Okay. You can say, why? If they are all wave equations, so that means why we need a quantum in the classical world. I have been jumping up and down saying that the quantum world and the classical world are so different. But you know what I'm saying? All you are saying is that they are identical because the same mathematics, the same physics. 到现在我一直在说古典跟量子非常的不同。怎么讲到现在为止都只看到你讲他们的同，因为同样的数学、同样的波方程式、同样的技巧、同样的现象，那为什么还要一个 quantum？Why do we need a quantum to differentiate from the classical world? You immediately have to observe they are different. Although the wave equation is the same. 你一定要立刻从这个式子上面，你只要盯着它 concentrate your thoughts on this equation for just 2 minutes, you will see right away quantum is different from classical. Just joking. This is not mediation course. But you can try mediation. When you look at the thing for 2 minutes, the thing will change. Okay. Square root of -1. It immediately changes the whole picture. Even though the mathematics are the same. But this constant I is square root of -1. Everybody knows square. -1. It has no root. It's I. It's a mathematical imagination by Gauss. 它是数学的想象。It's an easy way for mathematics to organize their mathematics. It does not happen in real world. No, it happens in real world. It's electron. And I say, then Professor Chen say, it is everywhere in quantum mechanics, quantum world. So I is everywhere in quantum world. That couldn't be true. Because when we measure, because physics is a measuring science, a measuring science cannot measure square root of -1, right? 物理是一个测量的科学，你再怎么测量都不会测量出根号负一嘛。So, my friend, they are so different. The Schrodinger equation and the classical wave equation. They are so identical. But they are so different. they are identical mathematically, but they are so different physically, in the physics sense, in physics interpretation. Remember, if this is I, remember, I haven't told you, or anyway, I haven't told you yet what psi is. This strange notation, the Greek word, Greek alphabet psi. First write down by Schrodinger, psi. Even now we still use psi to denote this wave function. What is it? We have no idea. Of course I have idea, but you have no idea. But you are not strange. Schrodinger, when he write down this equation in a romance with another girl, actually he doesn't know either. When he write down this paper, he doesn't know what psi is. 他也不知道这个 psi 是什么。Because he doesn't know how to measure square root of -1. So you see because quantum mechanics was very, very strange. Even though you don't know what you are calculating, you can calculate. 你不知道你在算什么，你会算。I think some high school teacher probably warn you that don't write down in the exam paper that you don't understand. You have to know what you are calculating to put an answer. You have to know what you are calculating when you calculate. No, it's not true. Schrodinger, when he's calculating, he doesn't know what he's talking about. Because he doesn't know what psi is. It's a complex number. You remember, if there is an I here, it's a complex number. This psi has a real part and the imaginary part. Okay, so so quantum mechanics is the first time physicists arrive at the mathematics first and the physics later. Let me put it in Chinese. 在物理的发展的过程之中，这是第一次数学先到了。我们先搞定的数学。We calculate, we calculate, we calculate, we calculate, and we get the calculate right answer. But what are you calculating? No, we don't know. We don't know. We don't know. See, 所以数学到1925, all the mathematics are already clear to everybody. Einstein, Planck, Schrodinger, Heisenberg, Bohr, that's the heroes we're going to introduce to you next term. Okay, that's another class of physicists, which should be heroes. I think you probably only know about Newton, but all these people are really heroes for our physicists. And where am I? Yeah, in 1925, all these people know how to calculate. It's clear, using all techniques with equation, but nobody knows how to interpret it. Let me show you why it is so hard to interpret so innocent and wave equation. 好，这个方程式看起来非常的天真可爱嘛，对不对？为什么你要 interpret 它？为什么有什么难？你既然已经会算了，为什么在解释上有这么大的困难呢？ Let me tell you that why the difficulty arises in some transparency. Okay, so maybe 5 minutes, and then we can have a break. You may say, how bizarre could quantum world be? Try me. Let me tell you how bizarre it is. Our encounter with microscopic world start mostly with the hydrogen atom, 氢原子. 氢原子, of course, we usually join in this way with an atomic nuclei at the center and electron orbiting around it, in circular orbit. It looks like this, okay? But immediately, you know that, and because so these circles has different energy from low to high. So therefore, if you write down their energy, it becomes an energy level like this. 能接，这个叫做氢原子能接，就是刚刚的 Schrodinger calculate the thing Schrodinger calculated the hydrogen atom energy level. So you probably have already know that in your high school physics, when an electron on the higher orbit moves down to the lower orbit, then the energy difference will be emitted in terms of a photon, okay? And that photon, you can see it from the emission spectrum. 放射光谱, this is called emission spectrum, okay? But right away, you know that this this is called Bohr atomic model. We'll go into very, very detail in next term. This Bohr atomic model, we right away know that it's correct. However, it's wrong theory. It's wrong, simply wrong. Why? Because the electron cannot orbit a nuclear center without emitting electromagnetic wave. 一个电子绕着一个原子核绕的时候，它就会放出电磁波。当它放出电磁波的时候 ，electromagnetic wave will take away energy, so that this electron has to move into lower and lower and lower, like Elon Musk orbit, the satellite. Will move into lower and lower orbits. Finally, it reached the nuclei, crashed. Okay, 掉进来了。It's inevitable. Okay, so that means the picture you draw here is incorrect because this orbit is not stable, unlike Musk's satellite. Okay, Musk's satellite is electric neutral, so 它不会放出电磁波。But electron is negative charged, so when it moves in a circular motion, it emits photon, it emits electromagnetic wave, and then it falls down to the nuclei. Okay, so it's wrong. Secondly, there is another problem. You say that because we see discrete spectrum in the emitting light, emitting electromagnetic wave, so that means the circle could only exist discretely. 好，它的这个能够存在的这些 orbit 呢，只能是一阶，而不是连续的。Okay, because we see that when you transit, the light it emits is discrete, 离散，就是它是离散分布的。Okay, why? Why the circle can only allow this one, and cannot be in between? 这又不是跑道，这又不是 running 那个 circle 的那个跑道，为什么不能跑在两个跑道的中间？没有道理啊 ！Again， 就像我们在讲到这个弹簧的时候 ，we say why couldn't we can adjust the amplitude to adjust the energy continuously？ 我们要多少就多少。Why could we not adjust the energy of the electron so that its orbit distribute continuously across the space? It should be possible. If it's possible, then the light it emits should be continuously distributed. 它应该是一个连续的光谱才对啊。But it's simply not true. Very famous hydrogen atom spectrum. It's almost like the energy quantization. This is the energy quantization. This is the energy quantization. That's why energy quantization is a basic feature almost happening everywhere in quantum world or in different world. Both here and both here. Okay. Why? Why is this so? So that means the microscopic world is very, very different from the macroscopic world. Because we know that satellites can operate continuously. Elon Musk 的人造卫星事实上是可以连续运作的嘛，它要到多高就多高，它要到多低就多低嘛，对不对？它的卫星的轨道事实上是可以连续选择的。微观的世界为什么不行？这个是让 that made the physicists at that time very nervous about the status of the physical world. When there is a problem, we usually have a prince to help us. Prince. Not Disney, but Prince. Yeah, he is really a prince. He is called Prince Louis Victor de Bois. Okay. 中文通常把它翻译成德布罗意 ，they use the English pronunciation that Broglie. OK， 所以呢 usually it's pronounced as 德布罗意 ，but I think it's pronounced as Dubois. OK, it's a prince. He is a prince of the house of Dubois. This house 就是法国的贵族，French nobility since 1600. OK, so he is the 7th duke. OK, before the 6th duke. The 6th duke is his brother. I think his brother is Robert. Robert Dubois. He's also a very famous physicist. Okay, and so when his brother is duke, 公爵，那 Louis is prince. So he's really a prince. And when he was prince, that's the days when he was active in physics. That's why we physicists usually remember Dubois as a prince. Okay, so it's really a prince in rescue. But he later inherited the dukedom from his brother, so he's the 7th duke of Dubois. Okay. Anyway, Dubois, for nobility, the usual way to solve problem is to make a mess of it. Okay. 解决问题的方法就是把它变得更糟，就是把它变得更糟。Okay, let's face. So he said, at that time, we know that already. Of course, I'll explain to you why. Light has been known to be also both a particle and a wave. Dubois said, why not electron? So electron could be then at that time, everybody understood electron as particles. And he said, why not wave? Well, with no reason. Well, Prince say. Of course, it's not no reason. Let me introduce Einstein here. So this is his PhD paper, but no French physicists know how to judge this paper because, well, electron is a wave? Come on, are you kidding me? Everybody knows electron is a particle since its discovery. And there are so many evidences, I will list it later, so many differences that tells us that the electron is really a particle. And then this prince from France told me, it's a wave. Come on, give me a break. So his advisors and the defense committee didn't know how to judge this paper, whether to give it a PhD and send the paper to Einstein, who is at that time was at Berlin. He said, well, we have this guy telling us this. What do you think? Einstein jumped on the paper, excited, say, that's it. That's the solution I've been looking for all these years. We now have a solution that don't need to revolutionize physics. 我现在终于有一个东西，我可以用来解决问题，但是不需要解决，不需要革命。如果 microscopic world is so different from macroscopic world, we really need a revolution. We need to find a new law. We need to find new government. You need to find a new law for the microscopic world. It's a revolutionary way. It's a revolution. But Einstein, the old guys at that time, we always thinking about Einstein as a revolutionist himself. 觉得他是一个革命派. No, but after 1905, he grew old very quickly. And at 1925, he was old already. Not 1925, 1915. He was old already. So he doesn't like a revolution. Truly. So he said, he jumped on the paper of Dubois. Say, this is the tool. I can use it to solve the microscopic world problem without revolutionizing. How to solve the problem in microscopic world? I told you. It's a wave equation, the same as old world. So if you accept electron is a wave, all the physical tools, all the mathematical tools are the same. No revolution is needed. You only need to change the flag. You only need to change the equation from classical wave equation to the Schrodinger wave equation. That's it. And all the technique is the same, concepts are the same. Okay, so that's why Einstein jumped on the idea. Of course, the Dubois paper also introduce some very beautiful argument to show that this PhD paper really worth a PhD. Okay, there must be some reason why this prince needs to introduce a wave into the electron. See, let me show you very quickly. If electron is a wave, let me imagine this electron orbiting the atomic nucleus in Bohr's atomic model. 哦，那个波尔的原子模型，电子绕着原子核在绕。No. We are talking about wave. So it's a wave propagating on the orbit. Naively, right? 简单说，我就看起来应该是这个波在这个轨道上面传播嘛。Okay? Oh, now you see the idea. If it's a wave propagating on the orbit, then that means the wavelength could not be arbitrary. Right? Because after one circle, it has to go back to the same value. It's this simple. Physics is simple. Because the wave, if it propagates around to the same point on the circle, the wave function must be the same. So that means your wavelength could not be arbitrary. Standing wave, 驻波的概念不就是这样吗？Standing wave. Okay, now so the orbit, this electron wave could propagate is either this, is either this, is either this, is either this or this or this. So that means we have a. So that's why we have a discrete distribution of states. Go back to this. So that's why we have a discrete state. At one stroke, the problem of atomic model was solved by Prince de Bois' ingenious idea. Could you see that? The solution is simple. Electron is not particle, it's wave. All solved. All solved. Okay, that's why you see why Einstein is so excited about this idea that electron is wave. Even though it sounds incredible, but it's actually very, very ingenious. Okay, it sounds very new, but it's actually old. 这个 idea 听起来非常的新，非常的不可思议，但其实是老掉啊，因为 wave equation, because wave equation physics has known it since old days, old friends. So electron is a wave, and wave is an old friend. So we don't need to introduce a new member to the club. That's the idea of Einstein. Okay. However, Einstein could not have it stay. He will be disappointed very soon. So let me show you. Okay, sorry, we'll need a break very soon. 2 minutes. Now, interference. If electron is a wave, then interfere for me. 你干涉给我看看嘛。Everybody knows the typical feature, a typical phenomenon of a wave is interference, double slit interference. I will talk about that in very, very detail next semester. You will see an interference pattern if it's a wave. And people, guys, of course you see an interference pattern. In this experiment, we throw out electron one at a time. And Feynman described this experiment in his lecture. And when I was your age, I always assumed that this experiment has already been done. However, this is so difficult. It was only done in 1989. 这个实验到1989年才真的有人做出来 by Mr. Tonomura Akira, Japanese in the Hitachi. Okay, but this picture is from Feynman's lecture. So Feynman 的 lecture 早就在讲这个，然后还真的画了一个这样的图。I feel cheated. Feynman 骗我啊！他在他那时代根本没有人做出这个实验出来，是骗人的。But now we know. 幸好1989年，Tonomura 先生真的把它做出来，不然我们会很伤心。Feynman 骗我们，大家懂我意思吗？好 ，Anyway， 好 ，OK， we don't need to go to detail, but this double interference is already done. It really is interference. When we send out, let me tell you why it is difficult. Because if you want to send out electron one at a time and detect it, it's difficult because the electron is so small, energy is so small. You have to amplify it several times. Where is the picture? Anyway, you have to amplify it in the process. It's the amplification that's difficult, not sending out electron. Okay, so, but Tomomura-san, at 1989, was good enough. The skill is good enough that he can send out electron one at a time. You can see the dot, this is one electron. One electron. Of course, that signal has been amplified so many times you can see it. Okay, so one electron, one electron. The point is they are sent out individually. 单独一个一个的出来 almost like in the musical, you introduce the character, the actors, one. So, but after several while, it becomes a wave. It becomes an interference. So, if you look at it, one picture, you of course will conclude electron is a particle. But if you look at to the end, you will say electron is a wave. So, this is a beautiful experiment that I hope will convince everybody. Electron is both a particle and a wave. one experiment in one stroke. A particle and a wave. Let me have a that's why you need to write down a wave equation. You have to endure the confusion that you don't know what psi is, but you have to go on and but they win the Nobel Prize anyway. But let me show you. And the key technique is eigenvalue problem. Okay. But here I should show this the transparency earlier. So this is the classical wave equation. This is the Schrodinger wave equation, and the technique to solve them and the solution are very, very similar. Okay. So, but to the disappointment of Einstein and the Schrodinger, to the surprise, excitement of Heisenberg and Bohr, all the revolutionaries. Heisenberg, Bohr 这些人呢是革命派。我到时候会告诉你们他们好玩的故事跟物理，那个革命的情境会非常的鲜明哦。那爱因斯坦跟普朗克呢是那个保守派。To the disappointment of the conservative like Bohr, like Einstein, Planck, and to the excitement of the revolutionaries like Heisenberg and Bohr, a particle, electron, could not be a particle and a wave. It's impossible. Well, I told you that electron is a particle and a wave. Now I'm telling you, and I will show you very soon in two transparencies. Electron could not, it is impossible for an electron to be both a particle and a wave. Break. 10 minutes.